On the morning of June 19th, 1944, Lieutenant Junior Grade Alex Vraciu climbed into the cockpit of his F6F Hellcat aboard the carrier USS Lexington. The aircraft beneath him had rolled off Grumman's assembly line in Bethpage, New York, exactly 47 days earlier. 47 days from raw steel to combat-ready fighter sitting on a carrier deck in the Philippine Sea. Vraciu had flown this particular Hellcat for less than a week, but he already trusted it completely. The aircraft was new, but it was identical to every other Hellcat he'd flown. Same controls, same visibility, same power, same feel. American mass production meant every aircraft was interchangeable, predictable, reliable. 700 miles to the west, aboard the Japanese carrier Zuikaku, Lieutenant Tetsuzo Iwamoto strapped into his Mitsubishi A6M Zero. The fighter had been hand-assembled at Mitsubishi's Nagoya plant over the course of several months. Each component carefully fitted, each joint meticulously inspected, each system individually calibrated. The Zero represented thousands of hours of skilled craftsman labor, built using techniques that emphasized quality over speed, precision over volume. It was a beautiful aircraft, and Iwamoto knew it intimately. He'd been flying this particular Zero for 8 months, nursed it through 2 previous battles, supervised its maintenance personally. Japanese fighters weren't interchangeable. Each one had its own characteristics, its own quirks. Pilots developed relationships with their aircraft because they flew the same one for months, sometimes years. Within 6 hours, both pilots would be engaged in the largest carrier battle in history. The engagement would be called the Battle of the Philippine Sea. American pilots would nickname it the Great Marianas Turkey Shoot, and the outcome would be determined not just by pilot skill or aircraft performance, but by 2 fundamentally different approaches to building fighters. One approach emphasized craftsmanship, quality, and engineering elegance. The other emphasized speed, volume, and industrial efficiency. One approach produced fighters that cost more in time, labor, and resources. The other produced fighters faster and cheaper while somehow making them better. The question that Japanese naval officers would spend the rest of the war trying to answer was simple. How did the Americans do it? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Japan's approach to building the Zero reflected a manufacturing philosophy that had served them well for decades. The Mitsubishi A6M was designed in 1937 by a team led by Jiro Horikoshi, one of Japan's most brilliant aeronautical engineers. Horikoshi's assignment was seemingly impossible. The Imperial Japanese Navy demanded a carrier fighter that could outperform any aircraft in the world while escorting bombers on missions exceeding 1,000 miles. The specifications called for a top speed over 300 miles per hour, a climb rate that could reach 9,800 feet in 3.5 minutes, exceptional maneuverability, and armament consisting of 2 20mm cannons and 2 7.7mm machine guns. And it had to operate from aircraft carriers, which meant reinforced landing gear, arresting hooks, and the structural strength to withstand catapult launches and arrested landings. No fighter in the world could meet those requirements in 1937. The specifications contradicted each other. Long range required large fuel tanks, which added weight. High performance required powerful engines, which also added weight. Carrier operations required strong airframes, more weight. Maneuverability required light wing loading. Everything pointed in different directions. Most engineers would have told the Navy it was impossible. Horikoshi said he would do it, but it would require innovations that had never been attempted in production aircraft. The Navy gave him approval to proceed. Horikoshi's solution was elegant and radical. He would build the lightest possible airframe that could still handle carrier operations. Every component would be optimized for weight reduction. The Zero would use a newly developed aluminum alloy called Extra Super Duralumin, which was stronger than conventional aircraft aluminum. This allowed thinner structural members, saving weight. The wing and fuselage would be built as an integral structure rather than separate components joined together. This saved weight by eliminating redundant joints and fittings. The wing itself would serve as the main fuel tank, with integral bladders built into the wing structure. This eliminated the weight of separate fuel tanks. The pilot would sit directly on top of the wing's center section, keeping the cockpit low in the fuselage and saving more weight. Every rivet would be flush-mounted to reduce drag. The landing gear would be precisely fitted into the wing when retracted, leaving no gaps or protrusions. The engine cowling would be hand-formed to create the smoothest possible airflow. The canopy would be carefully shaped and optically perfect. When the first prototype flew on April 1, 1939, it exceeded every specification. Top speed, 336 miles per hour. Climb rate, 9 minutes to 9,800 feet, better than required. Range with external drop tank, over 1,600 miles. Maneuverability was extraordinary. The Zero could complete a full 360-degree turn in roughly 16 seconds at optimal speed. No fighter in the world could match that. The aircraft was so light and the controls so responsive that pilots could execute aerobatic maneuvers that would tear apart heavier fighters. American pilots who encountered Zeros in combat reported that the aircraft seemed to defy physics, changing direction impossibly fast, climbing at angles that shouldn't be possible, hanging on their propellers in attitudes that should have caused stalls. The Navy accepted the Zero for production in July 1940 and designated it the Type 0 carrier fighter, named for the imperial year 2600, which corresponded to 1940 in the Western calendar. The Zero entered combat over China in August 1940, and it immediately dominated the skies. Chinese fighters couldn't compete. The Zero was faster, more maneuverable, had longer range, better armament. Japanese pilots racked up victory after victory. By December 1941, when Japan attacked Pearl Harbor, the Zero had earned a reputation as the finest carrier fighter in the world. And it was. Nothing else came close. But that performance came at a price, and the price wasn't just measured in money. Building a Zero required time, lots of time. The integral wing fuselage structure that saved weight also made manufacturing complex. Workers couldn't build the wing and fuselage separately in different facilities and join them later. Everything had to be assembled in sequence, with each step dependent on the previous step. The flush riveting that reduced drag required skilled workers spending hours countersinking rivet holes and carefully installing each rivet so it sat perfectly flush with the skin. One poorly installed rivet could create drag and reduce performance. The hand-formed engine cowling required craftsmen who could work sheet metal into complex curves without creating wrinkles or weak spots. The precisely fitted landing gear required machinists who could hold tolerances to a fraction of a millimeter. The integral fuel bladders in the wings required specialists who understood how to seal aluminum structures against fuel leaks. Every Zero was essentially hand-built by skilled workers who had trained for years to develop their expertise. Mitsubishi's Nagoya plant, which produced most Zeros, employed workers who took pride in their craftsmanship. They understood they were building fighters that Japanese pilots would trust with their lives. Quality mattered more than speed. If a component didn't meet specifications, workers would adjust it, file it, reshape it, until it fit perfectly. This approach produced exceptional aircraft, but it was slow. The first production Zeros took approximately 6 months from the start of construction to final acceptance. Skilled workers could reduce that time with experience, but even at peak efficiency, building a Zero required several months of labor. The cost reflected this investment in time and craftsmanship. Japanese records from the war indicate that a Zero cost between 55,000 and 120,000 yen, depending on the model and production year. Converting wartime yen to dollars is complicated because exchange rates were controlled and didn't reflect real purchasing power. But Japanese military procurement documents suggest the Zero represented a significant investment in both resources and labor. The aircraft consumed approximately 1,200 kilograms of aluminum alloy, much of it the expensive extra super duralumin. The Nakajima Sake radial engine cost roughly 40% of the total aircraft price. Instruments, radios, weapons, and other equipment added more expense. But the largest cost was labor. Thousands of hours of skilled craftsman time went into each Zero. Japan could accept these costs in 1940 because they had time and they had skilled workers. The nation had been building up its aircraft industry since the 1920s. Workers had trained under master craftsmen, learning techniques passed down through apprenticeship systems that emphasized quality and precision. Japanese manufacturing culture valued expertise. A skilled aircraft fitter who could hand-form aluminum parts to exact specifications was respected, well-paid, and took pride in his work. This cultural approach to manufacturing produced beautiful aircraft, but it didn't scale well. Training new workers took years. Expanding production required finding and training more skilled craftsmen. And once war began, time became a luxury Japan couldn't afford. The American approach to building the F6F Hellcat was fundamentally different, and that difference started with a man who had never built an aircraft in his life. Henry Kaiser was a construction engineer who had made his fortune building dams and bridges. When the war began, Kaiser saw that America needed ships, thousands of ships, and he proposed building them using techniques borrowed from construction rather than traditional shipbuilding. Instead of building ships from the bottom up, one piece at a time, Kaiser proposed prefabricating large sections in separate facilities, then assembling them like building blocks. Traditional shipbuilders said it was impossible. Ships required skilled workers, years of experience, careful fitting of each component. Kaiser said he could train unskilled workers to build standardized components in weeks, not years. The Maritime Commission gave him a contract to prove it. Kaiser's Liberty ship program revolutionized American manufacturing. He broke ship construction down into modules. Each module was built separately by workers who only needed to know how to build that specific module. A welder didn't need to understand ship architecture. She needed to know how to weld a specific type of seam on a specific type of joint. Repetition created expertise. After a month, workers became fast. After 2 months, they became precise. Kaiser's Richmond shipyard in California was completing Liberty ships in 42 days on average. The record was 4 days and 15 hours. 4 days to build a ship that traditional methods would take 6 months to complete. Grumman Aircraft Engineering Corporation watched Kaiser's methods with intense interest. Grumman was a relatively small company compared to Boeing or Douglas, but they had been building naval aircraft since 1930 and had developed a reputation for rugged, reliable designs. The F4F Wildcat fighter was tough and could absorb tremendous battle damage, but it was slower than the Zero, climbed slower than the Zero, and couldn't turn with the Zero. American pilots were getting killed in aircraft that couldn't match their opponent's performance. The Navy needed a better fighter, and they needed it fast. Grumman's chief designer, William Schwendler, began working on a Wildcat replacement in June 1941, 6 months before Pearl Harbor. The contract specified a fighter that could defeat the Zero. Schwendler understood that meant speed, climb rate, and enough power to execute boom and zoom tactics. American fighters couldn't outturn the Zero, so they needed to be able to dive in, shoot, and climb away before the Zero could respond. That required a massive engine. The Pratt & Whitney R2800 Double Wasp produced 2,000 horsepower, nearly twice the power of the Wildcat's engine and more than double the power of the Zero's engine. Schwendler designed the Hellcat around that engine, but Schwendler also designed the Hellcat for mass production, and that meant incorporating lessons from Kaiser's shipbuilding revolution. The Hellcat would not be hand-built. It would be manufactured using prefabricated components, standardized parts, and assembly line techniques that allowed unskilled workers to build complex aircraft quickly. The wing and fuselage would be built separately and joined together, unlike the Zero's integral structure. This meant different facilities could build different components simultaneously, then bring them together for final assembly. Separate factories could produce wings, while other factories produced fuselages. The production schedule wasn't linear, it was parallel. The Hellcat structure used simple, strong joints that could be assembled quickly without requiring precise hand-fitting. Rivets were installed with pneumatic guns by workers who learned the skill in days, not years. If a part didn't fit perfectly, it was rejected and a replacement was installed. American industry had enough aluminum that waste was acceptable. Speed mattered more than perfection. The engine installation was designed so that complete engine assemblies could be mounted to the airframe in hours rather than days. 4 bolts and a handful of connections. Disconnect the old engine, lift it out, drop in the new one, bolt it down. Any mechanic could do it with basic tools. Every component was standardized. Every Hellcat used the same engine, the same propeller, the same instruments, the same radios, the same guns, the same landing gear, everything identical. This meant spare parts were interchangeable. A damaged Hellcat could be cannibalized to repair other Hellcats. Workers didn't need to adjust or custom fit anything, parts either, fit or they didn't. If they didn't, you got a different part. Training workers was fast because they only needed to learn standardized procedures. Install this part using this method. Connect these wires to these terminals. Torque these bolts to this specification. Follow the manual, and you could build a fighter without understanding aerodynamics or aircraft design. Grumman's Bethpage factory in New York was reorganized around assembly line production. One building fabricated wings, another building fabricated fuselages, another building handled final assembly. Each building specialized in specific tasks. Workers in the wing plant didn't know anything about fuselages, and they didn't need to. They built wings, thousands of wings, all identical. Specialization increased speed. A worker who built the same component repeatedly became expert at that specific task. She could build wings faster than a generalist who built entire aircraft. The factory ran 3 shifts, 24 hours a day. Wings rolled out of one building, while fuselages rolled out of another. They met in final assembly, where teams installed engines, instruments, armament, radios, everything needed to transform components into complete aircraft. The first production F6F Hellcat flew in October 1942, just 16 months after the contract was signed. The Navy accepted it immediately and ordered full-rate production. By January 1943, Grumman was delivering Hellcats to fighter squadrons. By summer 1943, the factory was producing 500 Hellcats per month. One complete fighter rolling off the assembly line every 90 minutes, 24 hours a day, 7 days a week. At peak production in 1944, Grumman produced 644 Hellcats in a single month. That's one complete fighter every 68 minutes, around the clock, for 30 days straight. The cost reflected this efficiency. The F6F Hellcat's airframe cost approximately $35,000, not including the engine and government-furnished equipment. The complete flyaway cost, including the R2800 engine, instruments, radios, and armament, was between $50,000 and $65,000, depending on the specific variant and contract. That was roughly comparable to other American fighters like the P-51 Mustang, which cost about $50,000. The significant point wasn't that the Hellcat was dramatically cheaper than other American aircraft. The significant point was that American mass production could deliver a larger, more powerful, better-performing fighter for less money and in less time than the Japanese could deliver the lighter, less powerful Zero. The economics were shocking when you examined them closely. A Hellcat was bigger than a Zero. It weighed 9,200 pounds empty compared to the Zero's 4,100 pounds. It had a more powerful engine, 2,000 horsepower versus 950. It had heavier armament, 6 50-caliber machine guns versus 2 20mm cannons and 2 7.7mm machine guns. It had armor protecting the pilot, self-sealing fuel tanks, more sophisticated instruments, better radios. By every measure, the Hellcat should have cost more to produce. More materials, more components, more complex systems. Yet American mass production delivered these superior fighters faster and possibly cheaper than Japan could produce the simpler, lighter Zero. The explanation lay in industrial philosophy. Japan optimized for quality using skilled labor. America optimized for volume using process efficiency. Japanese craftsmen spent hours hand-fitting components to achieve perfection. American workers spent minutes installing prefabricated components that were manufactured to precise specifications. If a Japanese component didn't fit, craftsmen adjusted it. If an American component didn't fit, workers rejected it and installed a replacement. Japanese manufacturing culture viewed waste as unacceptable. American manufacturing culture viewed speed as essential. Both approaches had merit, but in wartime, speed won. The difference in manufacturing philosophy became apparent the moment combat began. On August 31, 1943, Hellcats from Fighting Squadron 9 flew their first combat mission, striking Marcus Island. The squadron had received their aircraft just weeks earlier. Most pilots had less than 10 hours in type, but the Hellcat was easy to fly. The hydraulic landing gear extended and retracted with the flip of a switch. The cockpit sat high in the fuselage, providing excellent visibility. The controls were responsive, but not sensitive. New pilots could master carrier landings in a fraction of the time required for the Wildcat. The aircraft was forgiving. It didn't punish mistakes the way high-performance fighters sometimes did. You could fly it hard without worrying about structural failure. The Navy's training command could take pilots with 300 hours total flight time and make them combat-ready in the Hellcat in weeks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese pilots faced a different challenge. The Zero demanded skill. It was light, maneuverable, and responsive, but it had quirks. The controls stiffened at high speeds to prevent structural failure. Pilots had to understand the aircraft's limitations because exceeding them could tear the wings off. The Zero couldn't dive as fast as American fighters. Pushing past the never-exceed speed could cause catastrophic structural failure. In combat, pilots had to constantly monitor their airspeed, their altitude, their fuel state, their ammunition count, all while fighting. The aircraft rewarded expertise, but punished errors. An inexperienced pilot in a Zero was vulnerable. An experienced pilot in a Zero was deadly. The problem for Japan was that experienced pilots were dying faster than they could be replaced. Before the war, Japanese naval aviators trained for 2 years before their first carrier deployment. They practiced navigation, gunnery, formation, flying, night operations, everything required for carrier warfare. The training was rigorous and comprehensive. Graduates were among the best-trained naval aviators in the world, but 2-year training programs required time, fuel, aircraft, and instructors. By 1943, Japan didn't have any of those resources in abundance. Training programs were shortened to 12 months, then 8 months, then 6 months. Pilots graduated with 100 flight hours instead of 500. They could fly and shoot, but they lacked the experience to survive against veteran American pilots. The economics of pilot training followed the same pattern as aircraft production. Japan optimized for quality, America optimized for volume. Japanese flight training emphasized individual skill development under the guidance of experienced instructors. American flight training emphasized standardized procedures that could be taught to large numbers of students quickly. Japanese pilots learned to exploit their aircraft's specific characteristics. American pilots learned to follow tactical doctrine that worked regardless of who was flying or which aircraft they were in. Both approaches produced competent pilots, but the American system could train 10 pilots in the time Japan trained one. Saburo Sakai, one of Japan's top fighter aces with 64 confirmed victories, was pulled from combat in early 1943 to serve as a flight instructor. He was shocked by what he found. The training program was overwhelmed. Instructors had too many students, classes were rushed, fundamental skills were being skipped because there wasn't time to teach them properly. Sakai later wrote that instructors were told to rush men through. Forget the fine points, just teach them how to fly and shoot. The pilots graduating from these abbreviated programs were brave and dedicated, but they weren't ready for combat against experienced American pilots flying superior aircraft. The Battle of the Philippine Sea on June 19th, 1944, demonstrated everything wrong with Japan's approach to aircraft production and pilot training. Japan committed 9 carriers to the battle. 3 fleet carriers, Taiho, Shokaku, and Zuikaku, and 6 light carriers. Those 9 carriers embarked 450 aircraft, less than half their designed capacity. Japan simply didn't have enough aircraft to fully equip its carriers. Worse, the pilots flying those aircraft were inadequately trained. The average Japanese pilot at Philippine Sea had perhaps 20 hours of combat flight time. Some had none. They were flying their first carrier operation against the largest, most experienced naval aviation force ever assembled. The American task force, commanded by Admiral Mark Mitchell, fielded 15 carriers, 7 Essex-class fleet carriers, and 8 light carriers. Those carriers embarked 956 aircraft, more than twice the Japanese total. The aircraft were superior. F6F Hellcats had a maximum speed of 380 miles per hour compared to the Zero's 340. The Hellcat could dive at 450 miles per hour without structural failure. The Zero's maximum dive speed was 360. The Hellcat was armored. Pilot armor, self-sealing fuel tanks, armored engine cowling. It could absorb tremendous battle damage and continue flying. The Zero had no armor. A single burst through the fuel tank would ignite it. Most critically, American pilots were combat veterans. The average fighter pilot in Task Force 58 had 200 hours of combat flight time. Many had 300 hours or more. They had fought at Tarawa, Truk, Hollandia, and dozens of smaller engagements. They knew their aircraft's capabilities. They knew how to exploit the Hellcat's advantages. They knew how to fight Zeros and win. When the battle began at 7:30 a.m., on June 19th, the outcome was never in doubt. Japan launched its first strike wave at 7:30. 69 aircraft. American radar detected them at 150 miles. Fighter directors vectored 40 Hellcats to intercept. The Hellcats hit the Japanese formation 40 miles from the carriers. They shot down 42 aircraft in the first 10 minutes of combat. The surviving Japanese aircraft continued toward the carriers and encountered a second wave of American fighters, then a third wave, then anti-aircraft fire from the screening destroyers and cruisers. 8 aircraft broke through to the carriers. They scored no hits. 4 aircraft returned to their carriers. Japan's first strike lost 94% of its aircraft. The second strike, launched at 8:56, fared no better. The third strike, 107 aircraft, achieved a single bomb hit on the battleship South Dakota, causing minor damage. By the end of the day, Japan had lost 300 carrier aircraft and their pilots. America lost 29 aircraft, most to anti-aircraft fire. The kill ratio was more than 10-1 in America's favor. Lieutenant Alex Vraciu personally shot down 6 Japanese aircraft that day, bringing his total to 19 victories. He landed back aboard Lexington with only ammunition for 1 gun remaining. When he climbed out of his cockpit, he held up 6 fingers for the photographers. The image became famous. Vraciu's Hellcat had 27 bullet holes in it from return fire. None penetrated the armor. The aircraft was repaired overnight and flew again the next day. That was American industrial power made tangible. Build fighters tough enough to absorb battle damage. Build them fast enough that losses don't matter. Build them cheap enough that you can afford to lose them. Build enough of them that you always have numerical superiority. The economic implications were staggering. Each Hellcat that rolled off Grumman's assembly line represented approximately $65,000 of American industrial output. That included the airframe, engine, instruments, radios, armament, everything. Grumman built 12,275 Hellcats during the war. Total program cost was roughly $800 million. That sounds like an enormous sum, and it was. But Japan was spending comparable resources to produce far fewer aircraft. The Zero program built approximately 10,000 of 937 aircraft during the war, fewer aircraft than the Hellcat program. And each Zero required more time, more skilled labor, and arguably more total economic resources when you accounted for the costs of training and maintaining the skilled workforce required. The mathematics became worse when you considered operational economics. A Hellcat could be maintained by mechanics with basic training. Standardized parts meant repairs were simple. Remove the damaged component, install a replacement, sign off on the work. Navy maintenance crews could swap an engine in a few hours, replace damaged wings overnight. Keep aircraft operational with minimal downtime. The Navy calculated that Hellcat availability rates averaged above 80%. Out of every 10 Hellcats assigned to a carrier, 8 would be flyable on any given day. That was remarkable for a high-performance fighter operating in a corrosive saltwater environment. Zero maintenance was more complicated. Hand-built aircraft had components that weren't perfectly interchangeable. A wing from one Zero might not fit another Zero without adjustment. Mechanics needed to be skilled craftsmen who could modify parts to make them fit. Engine maintenance required expertise because the Nakajima Sakai radial was a precision instrument that needed careful adjustment. Japanese carriers typically calculated availability rates around 60 to 70%. Out of every 10 Zeros assigned, 6 or 7 would be flyable. The difference between 80% availability and 65% availability meant American carriers could generate 30% more sorties with the same number of aircraft. The cost-effectiveness ratio became even more extreme when you factored in combat losses. Hellcats achieved a 19-to-1 kill ratio against Japanese aircraft. For every Hellcat lost in air-to-air combat, American pilots shot down 19 Japanese aircraft. That ratio reflected superior aircraft, superior pilots, superior tactics, and superior doctrine. But it also reflected industrial capacity. American pilots could be aggressive because they knew replacements were coming. Lose your aircraft in combat? There's another one waiting. Damage your aircraft? Maintenance will fix it overnight. Need parts? The psychological impact of knowing your side had unlimited resources was immense. Japanese pilots faced the opposite psychological burden. Every aircraft lost was difficult to replace. Every pilot killed was nearly impossible to replace. By mid-1944, Japanese naval aviation was in a death spiral. Combat losses exceeded production. Experienced pilots died and were replaced by inexperienced pilots who died even faster. Aircraft availability decreased as maintenance became more difficult. Spare parts became scarce. The industrial base couldn't keep up with attrition, and through it all, American production kept accelerating. The Battle of Leyte Gulf in October 1944 showed how complete Japan's defeat had become. Japan committed its remaining carriers as a decoy force. 4 carriers with almost no aircraft aboard sailed north to draw American carriers away from the main battle area. The plan worked. American carrier aircraft attacked the decoy force and sank all 4 carriers. But the sacrifice achieved nothing. American escort carriers in Leyte Gulf fought off the Japanese surface fleet anyway. The decoy operation cost Japan its last operational carriers for no strategic gain. Zuikaku, the last of the 6 carriers that attacked Pearl Harbor, went down on October 25, 1944. She sank because Japan no longer had enough aircraft or pilots to defend her. By November 1944, Japan had no operational fleet carriers. America had 28. The numerical advantage was greater than 500%, but the real advantage was systemic. American carriers were bigger, faster, better equipped. They had better radar, better fire control, better damage control, better logistics. They were supported by an industrial base that could replace losses faster than combat could inflict them. Task Force 38, operating off Japan in July 1945, included 17 fleet carriers and 6 light carriers. Those carriers embarked more than 1,500 aircraft. The entire strike force could be assembled, launched, and recovered in under 2 hours. Japan had nothing to counter that level of air power. The economic lesson was clear. Industrial capacity determined the outcome of the Pacific War. Japan entered the war with superb aircraft built by skilled craftsmen using techniques refined over decades. The Zero was a masterpiece of engineering, optimized for performance through careful attention to every detail. But masterpieces take time to build, and time was the one resource Japan couldn't afford. American mass production built Hellcats that were bigger, heavier, more powerful, and somehow cost less in time and resources than the lighter, simpler Zero. The difference wasn't American aircraft were better designed, though the Hellcat was an excellent design. The difference was American industry could build thousands of good aircraft faster than Japanese industry could build hundreds of perfect aircraft. Henry Kaiser's Liberty ship program demonstrated that prefabrication and standardization could revolutionize production. Grumman applied those lessons to fighter production. The Hellcat wasn't hand-built by craftsmen. It was assembled by workers who learned their jobs in weeks. Those workers could build fighters faster than Japanese craftsmen because they weren't trying to achieve perfection. They were trying to achieve adequacy at scale. And adequacy at scale, it turned out, was more valuable than perfection in small numbers. The cost comparison told the story. A Hellcat cost approximately $65,000 all in and took about 47 days from start of production to delivery. A Zero cost somewhere between 55,000 and 120,000 yen, which was difficult to convert to dollars, but represented a comparable or greater investment in resources, and took several months to complete. The Hellcat was larger, heavier, more powerful, better armed, better protected, and probably took less total economic investment to produce. That shouldn't have been possible. But it was possible because American industry had learned to optimize for volume using process efficiency rather than optimizing for quality, using skilled labor. The lesson extended beyond aircraft. American shipyards built more carriers in months than Japan built in years. American factories produced more ammunition, more fuel, more spare parts, more everything than Japan could match. The industrial advantage compounded over time. Every new factory made it easier to build more factories. Every trained worker made it easier to train more workers. Every standardized component made the supply chain more efficient. By mid-1943, American war production had become a self-reinforcing system that accelerated continuously. Japan never achieved that momentum. Every carrier they built consumed resources needed for the next one. Every worker trained took time from production. Every component required custom fitting that slowed assembly. The gap widened exponentially. In early 1942, Japan had 8 operational carriers. America had 3. By mid-1943, Japan had 6 operational carriers. America had 14. By mid-1944, Japan had 7 operational carriers. America had 32. By early 1945, Japan had 0 operational carriers. America had 39. The cost per victory told the final story. American carrier aviation shot down more than 5,000 Japanese aircraft during the war. The Hellcat alone accounted for 5,156 of those victories. At $65,000 per Hellcat and 12,275 produced, the total program cost was roughly $800 million. That investment produced 5,156 confirmed aerial victories, plus thousands of ground targets destroyed. The cost per aerial victory was approximately $155,000. Every Japanese aircraft shot down represented one less threat to American forces, one less trained pilot, one less drain on Japanese resources. The return on investment was extraordinary. Japan's investment in the Zero produced fewer returns at higher cost. 10,937 Zeros built at costs ranging from equivalent of perhaps $40,000 to $80,000 each in real economic resources. Total program investment perhaps $600 to $800 million in equivalent economic impact. Those aircraft achieved perhaps 3,000 to 4,000 aerial victories total during the war, though exact figures are debated. The cost per victory was significantly higher than the American ratio. And unlike American aircraft, which operated in an environment of numerical superiority with abundant spare parts and maintenance support, Japanese aircraft operated in an environment of scarcity where every loss mattered. The human cost made the economic comparison even more stark. American pilots flying Hellcats had an 84% survival rate in combat. For every 100 Hellcat pilots who went into combat, 84 came home. Japanese pilots flying Zeros had perhaps a 40% survival rate by mid-1944. For every 100 Zero pilots in combat, 60 died. The difference reflected aircraft capability, pilot training, tactical doctrine, and industrial support. American pilots flew aircraft that could protect them. Japanese pilots flew aircraft optimized for performance at the expense of protection. American pilots knew if they got shot down, search and rescue would try to recover them. Japanese pilots knew rescue was unlikely. American pilots could be aggressive because they had advantages. Japanese pilots had to be cautious because they were outmatched. Lieutenant Alex Vraciu survived the war with 19 aerial victories. He flew the Hellcat throughout his combat tour and trusted it completely. After the war, he described the aircraft as honest, reliable, and forgiving. It did what you told it to do. It didn't surprise you. It protected you when you made mistakes. And it gave average pilots a fighting chance against good opponents. That was the ultimate vindication of American mass production philosophy. Build aircraft good enough that average pilots could survive and good enough that good pilots could excel. Lieutenant Tetsuzo Iwamoto also survived the war. He was one of Japan's top aces, with more than 80 confirmed victories. He flew the Zero throughout the war and considered it a beautiful aircraft. But by 1945, he acknowledged that beauty wasn't enough. The Zero couldn't compete against the new generation of American fighters. It was too light, too fragile, too underpowered. Japanese industry had tried to develop replacements. The A7M Repu was designed to be the Zero's successor, with more power, better performance, and heavier armament. But only one prototype was completed before the war ended. Japanese industry couldn't scale up production of new designs while maintaining production of existing aircraft. They lacked the industrial capacity to do both simultaneously. American industry faced no such constraints. While Grumman produced 12,000 Hellcats, they also developed and began production of the F6F Bearcat, an even more advanced fighter. Chance Vought produced 12,500 F4U Corsairs. Republic produced 15,600 P-47 Thunderbolts. North American produced 15,000 P-51 Mustangs. American factories were producing multiple types of advanced aircraft simultaneously, all in quantities that exceeded Japan's entire production capacity. The industrial advantage wasn't just quantitative, it was systemic. American industry could innovate and produce simultaneously. Japanese industry had to choose between innovation and production. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.